about Chapter 3 in our textbook, Barton Faulkner's textbook, and Chapter 3 is discussing the kinetics of electrode reactions. And the kinetics of electrode reactions are somewhat similar to kinetics that you've probably already learned in other chemistry classes or maybe also in engineering classes. But the basic difference between most electrode kinetic processes and solution kinetic processes is the fact that the reaction occurs at an interface, usually a metallic electrode. So there is some slight differences in the form of the kinetic equations and also in how we deal with the result of the kinetic expression. Typically, when we're talking about electrode kinetics, studying electrode kinetics, we'll be looking at the current that flows at the electrode and using that current that flows as some sort of insight into the kinetics of the overall process. And also by examining the shape of the current potential curves, we can get information about the rate of the kinetic reaction or the kinetic process, but also the mechanism that underlies that electrode reaction. In other words, where does the electrons get transferred? Is there a chemical reaction before or after electrons get transferred? Is there more than one electron transfer? Those are the sorts of things we can examine by looking at current potential curves and understanding the concept of electrode kinetics. Previously, we considered electrode reactions that were at equilibrium, that were reversible. And if you remember, we drew current potential curves, something like this, where we could draw, for example, with a solution that had only O present in solution, we'd get this nice sigmoidal shape, and we call that plateau. That was a limiting current, and we said that if we looked at the half wave potential there, that was the standard reduction potential, or maybe the formal potential. Okay, on a reversible or sometimes called Nernstian process. Nernstian, can't spell. Nernstian. And basically a reversible process or Nernstian process suggests that we've got equilibrium is maintained at all points on that current potential curve. So we can use the Nernst equation and simple concepts of mass transfer to derive that equation, or derive that current potential curve. So what if you know what you can see here is very easily is that the current is proportional to somewhat proportional to potential. It's not linearly proportional to potential, but there is a strong dependence on the current flow on the potential of the system. So any description of current potential curves has to include some sort of a potential dependent parameter. And we've also already noticed that the rate or velocity of an electrode reaction is proportional to the current. So by monitoring the current, we can get some information about the rate or velocity of an electrode reaction. Now for a Nernstian situation, what we're basically looking at is the rate or velocity of mass transport to the surface. Where in a kinetically limited situation, we're going to be looking at either situations where the kinetics completely are determining the rate or velocity, or a mixture of mass transport and the kinetics will be determining the rate or current that we see on the electrode surface. So by looking at the curves again, we'll get information about the rate of mass transport or the rate of kinetic reactions. Most electron transfer processes are not, and I'll use sometimes the abbreviation ET to stand for electron transfer. So if you see ET, just think electron transfer in your head. So most electron transfer processes are not reversible at time scales of interest. And that's an important thing to keep in mind, is that almost every electrode reaction can be made reversible if we allow for a sufficient amount of time to pass for the reaction to achieve equilibrium. But in general, we may not be willing or able to wait for the equilibrium to take place. So most situations are not at equilibrium, so it's really, we do have to really understand kinetic processes on electrodes. what happens when we draw non-equilibrium electron transfer processes and we plot them as current potential curves? What we see is that from the initial potential, current potential curve may be reversible again as shown, but as the electron transfer rate drops off, what we see is a shift. And you get a set of curves, for example, as k, which is the rate constant, becomes smaller. And so essentially what's happening is that we start to see an increase in the overpotential for the electrode reaction. So as the rate constant decreases, becomes smaller, the overpotential is larger. What is clear from initial studies of electrode kinetics is that if you look at the initial part of this wave, say in this region right here, perhaps I should use a different color. If you look at this part of the wave, what you see is that the current is experimentally noted to be proportional to an exponential function. And we can parameterize that exponential function by saying the current is proportional to the exponential function that's to minus b or some parameter that we can adjust, and the potential of the electrode that we've added to. So we get this exponential aspect of the current flow. That's at the foots of the wave. As we go towards the mass transport limit, as we go to where it plateaus off, that current exponential function no longer applies. But you can see that's an exponential increase in current on all those little shifts. Okay, so any situation where we look at electrode reactions and kinetics, we're going to be interested in seeing what that exponential function is doing for us. All right. Well, whenever we're looking at electrode reactions, we can describe a kinetic process like so. Suppose we have a reaction A going to B. Well, A and B can be at equilibrium or not. But if we allow A and B ever to come into equilibrium, we have to think about the fact that there will be two rates of reaction. One rate would be given, it would be characterized by a rate constant we'll call K sub F, which is the rate of conversion of A to B. And then there's a back rate, KB, which is the rate of conversion from B to A. And what we've probably learned from other chemistry courses is that if we plot, or if we say KF over KB, the ratio of those two rate constants is equal to the equilibrium constant. And it's generally proportional to the concentration of B over concentration of A, depending on the basic reaction process. But in other words, this is the important thing we're talking about. KF over KB is equal to the equilibrium constant. So we've already talked about equilibrium processes, and we can see by looking at those rates that it doesn't matter with the relative values of those values. KF and KB may be very large, or KF and KB may be very small, but you can imagine that the ratio of very large KFs and KBs could be equal to the ratio of two very small KFs and KBs. So KF and KB are sort of an indication of the facility at which a reaction can achieve equilibrium. If KF and KB are very small, then the rate of achievement of equilibrium can be very small indeed. So things that are hard to achieve equilibrium generally have small rate constants. Things that have large rate constants can achieve equilibrium very, very rapidly. And so by understanding equilibrium and seeing if some things are at equilibrium, we sometimes can get an understanding of rates of reactions. Okay. Well, let's take a look at an electrode in solution. And let's draw a diagram of an electrode, like I always do, with a little bit of a dashed line there. And if we have an oxidized molecule in solution and a reduced molecule in solution, electrons can go perhaps into the oxidized molecule, making it reduced, and electrons can come out of the reduced molecule, making it oxidized again. And so the electrons that are going into an oxidized molecule are basically cathodic type processes. We're doing a reduction when we put electrons into an oxidized molecule. And the current that would flow for electrons being transferred would be an anodic process for taking electrons out of the reduced molecule. And so what we observe as a current in any particular case, actually we'll just say current in general, is equal to the sum of those two microscopic currents, the cathodic current and the anodic current. In other words, if we look at the current that's flowing totally, it's going to be the sum of the, actually be the sum, not the difference, the sum of the cathodic currents and the anodic currents. When we write the anodic current as having a negative thing. So we can have both currents flowing at the same time, but the sum may be, say, 0, or it may be I sub L, or any other value of the current in between those 2 points. Okay. In any case, we only observe the net current. We don't see the individual the components of the current. We don't see the anodic or cathodic parts of the current that flows. And that's an important thing to remember. Anytime we're looking at electrokinetics, we're observing an overall current flow, not the individual components of the current flow. So any description of kinetics has to be able to describe those individual components as parts of the reaction. Let's take as an analogy a typical homogeneous process. Again, let's take A to B. Now, A going to B can be characterized again by kinetics, but we can also say, well, there's a rate, a velocity in the forward direction and a velocity in the reverse direction. And for a first-order process, the forward reaction velocity is going to be equal to a rate constant times the concentration of species A. And the velocity in the reverse direction is going to be the backwards rate constant times the concentration of B. And again, the net, what we actually observe, is equal to VF minus VB. So in this case, this is basically what they'd call a homogeneous reaction generally. In other words, if we had these A and B as species in solution or as gas phase molecules, that would be a homogeneous solution, a solution where the reaction occurs in a isotropic system. It's uniform in all directions. Whereas most electrode reactions are heterogeneous. There is not an isotropic system. We have an interface where the reaction occurs at. So it's not uniform in all directions. And so we'll be looking at heterogeneous kinetics. Now, heterogeneous kinetics are first order as a rule. And so by looking at first order homogeneous kinetics, we can understand some aspects of first order heterogeneous kinetics. Again, the equilibrium constant for this homogeneous process is going to be equal to Ca or Cb for this first order process, and that's going to be equal to Kf over Kb. Also note that V net is equal to 0 at equilibrium. In other words, there's no net flow there's no net reaction velocity at equilibrium conditions. In other words, the sum of the forward and the back has to be equal to 0. That doesn't mean there's no reactions going on. In fact, that's the very characteristic features of chemical equilibrium, is that it's a dynamic equilibrium. We have reactions occurring at the forward rate and the reverse rate at the same net velocity. So VF, Kf times Ca is always equal to Kb times Cb at equilibrium. When things are not at equilibrium, one of those terms becomes larger or smaller than the others, and that is what we see as a net production of, say, B, or a net production of A. Okay. Now, let's concentrate, though, on heterogeneous reactions. A term that we've already used to describe a velocity of a heterogeneous reaction is this one, where we have, say, the cathodic current over NFA, we can describe as a cathodic velocity. And we can say, well, that cathodic velocity is equal to a rate constant. Let's call it not Ka, let's call it K sub C. K sub C times some function of E, potential, times the concentration of species O at the electrode surface. Why do we have a function of E in there? Well, we've already seen that any description of kinetics has to include the equilibrium case. And so we know at equilibrium that the current is strongly dependent on the potential. So any description of the rate constant or any description of the current flows in a heterogeneous reaction has to include a potential function. And notice something else that's not as convenient as in homogeneous kinetics. We have to consider the concentration of that species, that's say it's oxidized species, at the interface itself, not the concentration out in solution. So whatever the solution is that we've made up, that's not as critical as what the concentration is at the electrode surface. And that's not always directly available. So that's an important distinction between homogeneous and heterogeneous processes. And likewise, we can draw or write down an equivalent process for the anodic case, where the velocity is equal to the rate constant in the anodic direction times C sub r, again at the electrode surface. Now for all of these cases, the rate constant is going to be equal to centimeters per second, and the concentration in moles per cubic centimeter. So usually, you know, when we do chemistry and analytical chemistry, we're talking about moles per liter. Now, moles per cubic centimeter is a smaller amount than moles per liter. Moles per liter would be moles per cubic decimeter. So concentration is generally a factor of 1,000 smaller in numbers. All right. So let's see if we can derive an expression for the function of E that is consistent with experimental results. And what we're going to do is going to try to derive an expression that's what we call semi-empirical. It uses the experimental results that we've already noted to derive a parameterized equation for the electrode kinetics. So let's take and see if we can derive a parameterized semi-empirical expression for this electrode process. Species O plus some number of electrons going to species R, with rate constant Kf for O to R and Kb for R to O plus Ne. So any theory that we derive must have a few certain conditions. One is that it must conform to the Nernst equation. So any equation that we derive must at long time, at equilibrium, under equilibrium conditions, approach the Nernst equation. And remember the Nernst equation. If you don't remember the Nernst equation by the time you finish this course, you're not doing very well. So here's our Nernst equation. Notice the Nernst equation has the bulk concentrations in it, not the surface concentrations of it. Okay. Also, our semi-empirical theory must also include our experimental observation about the nature of the current as a function of potential. And we noted that the current is parameterized in this function. We saw that A times an exponential function of the over potential over B, where A and B are adjustable parameters. In other words, early workers in electrochemistry, before a theory of kinetics were even developed, they noticed that this general expression was true. They could put in a value for the over potential, which again is the shift from equilibrium potential, and two parameters could pretty much describe the current potential curves. So this part here is our empirical observation about the nature of the current and potential. So given this, we can put in our potential dependence into the system. And we can say that starting out, we'll start writing down the equations that we've already really got. The cathodic current is NFA. We're always going to include those electrical terms and the area term, times Kf times the concentration of O at x equals 0. Now that's not anything new. That's already from above. We've got that. X equals 0. So what is Kf? That's the big question. And Kb. Again.
Kf is Kc?
Kf is, we can, what we're going to do is we're going to use Kf and Kb to stand for previously, well, I said Kc and Ka. Now what you'll see, the reason I switched is that in the literature you'll actually see sometimes Kc, sometimes Kf, depending on the author. In Bard and Faulkner they use Kf and Kb pretty much throughout. All right. Sometimes they'll also use K sub O, K sub R, indicate the same sort of thing. Usually it's fairly apparent what they mean by just observing the treatment. So what I'm going to do to try to develop a theory is first I'm just going to write down the answer, and then we're going to see how we can get to the answer by deriving it. That makes it a lot easier to derive it sometimes. So let's just write down the answer that we're going to derive. Kf is equal to what we call a standard rate constant, K0, an exponential term just like we expect, a constant we'll call alpha, and we're going to use a small f, E minus E0 prime. So we're going to use the formal potential generally, because most of the situations we can substitute a formal potential for a standard potential anytime. And so we've made some substitutions just for ease of writing things down. We're going to use a small f to stand for F over RT, because those are generally constant in any of the situations, although the temperature can change, but usually the temperature is held at room temperature. Kb, K0, E, 1 minus alpha, NF, E minus E0 prime. So the exponential term has all these parts to it. K0 and alpha are our adjustable parameters. So this is our parameterized equation, semi-empirical equation. K0 called a standard rate constant. Sometimes you'll see it alternately written as K sub S or even K sub SH. Both of those are usually in older literature. You'll see it, although some experimenters still use K sub S. But usually you'll see K0, K sub K0. And alpha is usually called a transfer coefficient. And sometimes it's called a symmetry factor. Another M there, I think, is needed. For reasons we'll explain in a little bit. Sometimes you'll see alpha written as in a complementary form as beta, and particularly for European electrochemists, I don't know why exactly they chose beta instead of alpha, but sometimes you'll see that as well. Okay. Standard rate constant, again, has units of centimeters per second. The alpha transfer coefficient is dimensionless, has no units.